Greetings, this is Unit 8, Day 3, the comparison test and alternating series tests. So what we are looking at is we're going to be kind of looking at these series, and we need to determine whether they converge or diverge. So if you have your notes, and then you may also want to have your kind of summary chart here of the test, that hot pink one. And so let's take a look first what the comparison test is on here. So it's the one at the very bottom, and again we're trying to determine if a particular series converges or diverges. In the comparison test you would say, well, I'm probably going to be comparing it. So what the comparison test says, basically, if you know something is smaller than something that already converges, then it also converges. So think about it this way. If I said, well, you know, Sally is short, and her brother is shorter than Sally, well, then you know her brother is short as well. So it's kind of what it's saying. So we're going to take something that looks almost like something that I know what it's doing by some other test, and then by the comparison test I can make a conclusion. So here it basically says smaller than something I know what it does converges, right? Smaller than small converges. And then if something diverges and you know that it's bigger than that. So if I say, well, Sally is rich and Johnny has even more money than Sally, then you know Johnny's rich too. So if that diverges, then something bigger than diverges also diverges. So that's all the comparison test is saying. And you're like, well, if I know, how am I going to know what the first thing is doing? Well, hopefully by some other test. So if you take a look at the first example, in the first example, you have the summation here, and it almost looks like a p-series, right? So a p-series would be if you had a number over some n raised to a power. Well, that's not exactly what's going on here, but I wish that it was just 1 over n cubed. So basically what I'm saying is I'm going to compare it to 1 over n cubed. And I know that the summation of 1 over n cubed, which I just called b sub n, I know that that converges by the p-series test. And again, if you need to kind of reference that hot pink sheet, we know that for the p-series it converges when p is greater than 1. And in that example, my p-value was a 3, so we know that that converges by p-series test. Now, what else can I say about this? Well, I need to be able to compare this to my 1 over n cubed. Well, I know that this, which I'm just going to call a sub n, I know that that's going to be smaller than my b sub n. How come? Because if I add 1 to the denominator, the whole thing decreases in magnitude. So I know that a sub n is less than b sub n. And then it meets the conditions for my comparison test. So since a sub n is smaller than b sub n, and if I know that b sub n converges, I know it converges by some other test, I can also conclude that a sub n converges by the comparison test. So that's what I did there. Okay, so let's take a look at a couple more examples. I'm just going to slide this on up. All right, so now I want to take a look. Look at these two bottom ones here. So we've got, this is my new a sub n. So again, I'm kind of looking at the meat of the sigma there. And this plus 2 is really what's throwing it off. So I'm like, well, what if I compare it to just this 1 over 3 raised to the n? And that isn't exactly, you know, how I want it to look either. And you're like, well, it's p-series. No, it's not. It's not n raised to a power. It's a number raised to a power. So the trick you can use here is knowing that 1 raised to any power is still 1, right? 1 squared is 1. 1 cubed is 1. So I can get away, because that numerator is a 1, okay, I can get away with writing it like this. And if you're not sure, think about it. If you have an exponent out here, it goes to each part, the numerator and the denominator. So that's equivalent to 1 to the n divided by 3 to the n. Well, 1 to the n is just 1, and that's an important concept that's going to kind of travel through this unit. So keeping in mind that 1 raised to any power is just 1, we can rewrite it like this. And the advantage of writing it like this is now I see it as something that looks geometric. Okay, so I know with a geometric, and again, if you need to reference that pink sheet, kind of have that pink sheet handy, geometric is on there. So geometric, okay, that's going to converge when my common ratio is less than 1. Okay, the absolute value of it. But here it was, I believe, a positive. So, okay, so now I'm saying that I know that the summation of b sub n, that one that's almost like the one I want, right? I know that this converges by geometric series, right? It's geometric, my r is 1/3, and that's less than 1. So I know that this thing converges. Well, now I need to say, how does that help me? Well, how would I compare these two, right? My a sub n and what I'm calling b sub n. Well, if I wanted to compare those, I know that if I add 2 to the denominator, that's going to make the denominator larger, which makes the whole thing smaller in magnitude. So I know that this, what I'm calling my a sub n, is less than my b sub n. Okay, I know that. And since that is true, okay, then I can say that the summation converges by comparison test, because smaller than small is small, right? So if that thing converges and this thing's even tinier, then I know that also is going to converge. I kind of made a note here. If you weren't sure, you can kind of start extrapolating it. So if you wanted to extrapolate this a sub n, start by plugging in 1, right? Because I start by plugging in that denominator, or by plugging in this bottom number here. So if you plug that in, you get, 3 plus 2 is 5, right? So I get 1/5. And then if you plug in a 2, you get 9 plus 2 is 11. So if I generate the first 3 terms there of my a sub n, and then I generate the first few terms of my b sub n, okay, you can see right away that those are going to kind of, which one's going to be smaller, which one's going to be bigger, okay, by comparing them that way if you weren't sure. But again, you should just kind of have the concept. If you add something in the denominator will be getting bigger. As your denominator gets bigger, the magnitude overall gets smaller. All right. And then let's look at this one down here. So we've got the summation. And again, you're like, well, if it was only a 1 over square root of n, I could rewrite that as a power, and then it'd be a p-series question. So I want to compare it to what I'm going to call my b sub n of 1 over square root of n, and I know that I can rewrite square root as n to the 1/2 power. Okay, so these are the two that I'm working with, and what can I tell you about b sub n? Well, if I would have put this on your homework, yesterday, you'd say that 1 over n to the 1/2 power, that's going to diverge by the p-series test, because here my p-value is 1/2, and the p-series test diverges when the p is between 0 and 1. So that thing is going to diverge. And so now you need to say, okay, how does b sub n compare with my a sub n? So, well, this time I'm going to be subtracting in my denominator. Well, when you subtract from your denominator, okay, it's going to make the overall thing larger, okay? So when you're subtracting from your denominator, think about it. If you had, 1/3 and you subtract from it, you're going to get 1/2. 1/2 is bigger than 1/3. So now I can say that my b sub n is less than a sub n, or in other words, a sub n is greater than b sub n. So just be careful in how you're wording it. Remember, if Sally is shorter than Johnny, then Johnny is taller than Sally. So when I wrote it, this a sub n is going to be larger in magnitude than b sub n. And again, if you really get stuck, you could start to extrapolate. My goal is that you don't have to do this part of work over here. Hopefully you can just get it conceptually. But if you get really stuck, just start extrapolating it out and kind of comparing. So if we know that b sub n diverges and a sub n is even bigger, right? If this guy's rich and the other guy's has even more money, then they're both rich, okay? So now we can conclude that the a sub n also diverges by the comparison test. All right, now let's take a look at the alternating series test, okay? So an alternating series is a series whose terms are alternately positive and negative. So, for example, you go here, you start with a positive, and then it's a negative, positive, negative. Or you start negative and you go positive, negative, positive. So it just alternates. So what you want to do is look for the last term of it. Not like the last one, but you're going to be looking for a term that has a -1 to a power or a -1 to an n plus 1. You're going to kind of look for those. when we're kind of talking about, when we're working a problem, we're trying to figure out, oh, what test do I use? That's going to be your big clue. That's what you're going to be looking for. The alternating series test is a little bit obvious because it's going to have a -1 in there somewhere. So keep your eyes peeled for that, and if you see it, then the alternating series test would be a good one to try to use. And similar with our other test, there's going to be conditions that have to be met. Okay, so you're going to look for that -1, so that kind of is a clue that that's a good test. And the conditions that you want to write, the limit as n approaches infinity is 0. And you're like, wait a second, that's familiar. Well, basically, that's your divergence test, but basically, if you get 0 in the divergence test, it's inconclusive. So, and again, I'm hoping that you may not even try to do your divergence test once you start seeing those -1s, because that would be a clue like, oh, probably going to have to use alternating series. But basically, if your divergence test fails, okay, I shouldn't say fails, is inconclusive, that needs to happen for the alternating series test. And then also, this says that a sub n plus 1 is less than a sub n for all n. So as you're going, to the right-hand side of that extrapolation, they're smaller as you go, okay? And that's in magnitude. Really, it should kind of be absolute values there. So we're looking for alternating signs. We're looking for it to decrease in magnitude, okay? And also have a limit of 0. And you could think of that as the divergence test would be inconclusive on this. Now, just like with our divergence test, the divergence test can only be used to prove divergence. Well, our alternating series test cannot be used to show divergence. It can only be used to show convergence. And if you kind of reference back to that pink sheet again, the alternating series test here, you cannot be used to show divergence, okay? So, hopefully if you're using this, it's going to converge, okay? It would just be inconclusive. So that's just kind of saying that. Note that it doesn't say that you can't conclude that it diverges by the alternating series test. The alternating series test can only be used to prove convergence. If the limit does not equal 0, then you'd be like, oh, this diverges by the divergence test. And hopefully you might even check this condition first, because then you'd be done, okay? So we have that going. All right, now let's take a look at this example. Oh, and I'm stuck there. Okay. All right, so determine whether the following series converge or diverge. So then we've got some examples, and make sure we are making a concluding statement so we get all of our points that we need. Okay, so I'm taking a look at this right away. You're like, oh, this looks terrible. No, it's not terrible, because I see that -1 raised to a power, right? It meets those, oh, I see it. So again, where I was saying before, oh, try the divergence test first, you might not actually do that here, because you'd see that -1 and you'd probably go right to your alternating series test. But you'll notice that if you did your divergence test first, you'd be done. But let's just kind of do it as if we were doing the alternating series test. So, is this thing alternating? Yep, it's got that -1, so you're going to be alternating in sign. So check, it meets that requirement. Is it decreasing? So as you increase, the ends that you're plugging in, this thing is decreasing. This denominator is going to be getting bigger and bigger, so the overall is going to be getting smaller. And if you needed to plug in 1, then plug in 2, then plug in 3 to kind of get some things there, if you needed to extrapolate it out, then by all means, go ahead and do so. And so then I get to that third requirement, and this is me kind of checking for that decreasing here. So at n equals 1, I plugged in and got a 1. At n equals 2, I plugged in and got, -0.66. Need a negative sign there. And then if I plug in 3, I get this. So you can see that it is indeed decreasing. So if you needed to check for that, you can. And then I'm going to take the limit as n approaches infinity. So notice this is my divergence test. That's what the divergence test says to do. So I'm kind of going to go ahead and do this. And I'm like, all right, well, when I go to plug in infinity, I get infinity over infinity. And I'm like, ugh, drats, right? So then I'm like, all right, let me apply L'Hopital's. So the derivative of the numerator. Now this is where you're going to have to use kind of a neat little math trick here, okay? So the idea is that you really look at this part right here, -1 raised to the n plus 1. So that's either going to be +1 or -1, right? It's going to be a a positive 1 if that exponent ends up to be even, and negative 1 if it's going to be odd. So either way, when you raise that, you're going to get a positive 1 or a negative 1. So if the coefficient, essentially, is what we're saying, on this end term is going to be either a positive 1 or negative 1. So when you take the derivative, because that's what I'm trying to do here, I'm trying to apply L'Hopital's, which says that the derivative of the numerator. So since this n is to the first power, the derivative of it is whatever that coefficient is. Well, so that means that it's either going to be a positive or negative 1. So that's why I put that. It's either going to be positive or negative 1. So I'm not sure. But it's going to be one of those two things. Then the derivative of the denominator, because again, L'Hopital says the derivative of the numerator divided by the derivative of the denominator, right? We want to take the limit as that approaches infinity. The derivative of this denominator is just a 2. Okay? So what I have going on here is that when I go to take the limit as n approaches infinity, well, there's no more n's. Okay? So when I go to quote-unquote plug in here, I just get that the limit is either going to be positive or negative 1/2. So although I don't know whether it's going to be positive 1/2 or negative 1/2, depending again on if that exponent is going to be even or odd, I know that positive 1/2 and negative 1/2, either one of those, it definitely doesn't equal 0. So I know that this thing then diverges by the divergence test. Okay? So here's like, well, why didn't we just try the divergence test first? Well, so you would have tried the divergence test first and it would have worked on this one, okay, and you could have been done. But if you had an example where something ended up converging, like the next one, then you would say, oh, well, it was inconclusive, and then you would have to go to the alternating series anyway. So this one then, just remember that the alternating series, if you get something that doesn't work, but it's an alternating series, you have to conclude that it actually diverges by the divergence test. So then we go to, all right, let's take a look at page 3. Okay, so for the next example, we take a look at it, and you could try to, so say you just tried to do the divergence test right away. And again, I would, as soon as you see that negative 1, you should be thinking alternating series test. But, so say you try to do the divergence test first, you would take the limit as n approaches infinity, and you'd say, okay, well, you could just kind of, when you do that, you'd get this raised to the n over this. Well, when you quote-unquote plug in infinity, again, you're going to use that same trick where negative 1 raised to the infinity, well, it doesn't matter what n is. When you raise 1 or negative 1 to a power, you're either going to get positive 1 or negative 1. So you have this there, and then when you square infinity, it's huge. So you get either positive 1 or negative 1 divided by infinity. Either way, it's still 0. So this would yield an inconclusive result via the divergence test. So then you're kind of back to like, okay, well, what other test can I use? And then hopefully you see that negative 1 and you're like, okay, this is a candidate possibly for alternating series. So you kind of go through and make sure it meets the other requirements. You say, is it alternating? Yeah, you've got that negative 1 there. Is it decreasing? Well, let's take a look. If you plug in n equals 1, right? So if you plug in n equals 1, you end up with negative 1 there. Okay. Oh, I'm sorry. Was it an absolute value or something? What's going on? Yeah, I'm kind of looking at the magnitude of it. So that's kind of why I'm thinking of that as the absolute value. So if you go from, 1 to 1/4, you're definitely decreasing in magnitude. So since I'm alternating, yes, you can see it went from negative to positive, right? So it's alternating, yes, decreasing. And when you're thinking about the decreasing, again, you're looking at the magnitude. That's why I kind of put those absolute values there. So I'm decreasing, yes. And then you take the limit as n approaches infinity, which if you did the divergence test first, you'd already be done. But, as soon as I saw a negative 1, I'd probably start on the alternating series test anyways. So when you take the limit as n approaches infinity, you would get 0. So it meets the conditions and it converges by the alternating series test. And you can do that there. Okay, so the next thing we're going to talk about then is our error. So the alternating series error bound, the ATS remainder theorem, sometimes as it's referred to. Basically, it has to kind of meet those terms. It has to be alternating, it has to be decreasing in magnitude, and it has to be approaching 0. So, all those things we just talked about. So this is where students get a little bit confused. So if the true sum, so this is the dead-on exact accurate sum, okay, and the sum of the first n terms is s of n, then the error. So the error is whatever the true sum is minus what the sum is of the ones that you can add up. okay? And we say that is less than the absolute value of the first omitted term, okay? So basically, these show up in the multiple choice section on the AP exam. Okay, let me kind of scooch that up one more time. Oops, sorry. Okay. Okay. All right, so let's just take a look at this first thing. So again, right away, you see that -1 raised to a power. You're thinking alternating. So if you kind of started to extrapolate that out, so if I plug in a 1, right? So if I plug in a 1, this is -1 squared is 1, 1 factorial, okay? And then I plug in a 2. So I get to there again. I plug in a 3, plug in a 4, plug in a 5, okay? So you can kind of keep going there. That's what it looks like if you needed to extrapolate it out. It says approximate the sum S using the first 4 terms of the sum. So if we're approximating the sum, then all I had to do is extrapolate it out, okay? And then 1 factorial is 1, so I get 1. And then 2 factorial is 2. 3 factorial is 6. And 4 factorial, so 4 times 3 is 12, times 2 is 24. So if I needed to kind of approximate the sum with the first 4, and they'll tell you in the problem, like, you know, the first, 4 terms, 6 terms, or whatever. Hopefully it's not more than like 4 or 5. So then you'd have to add those together, and here I get a common denominator, and then you can reduce it in there. I think I just kind of used my calculator, but if you had to, you'd be able to get a common denominator and kind of estimate or approximate the sum of this, okay? So this is where the multiple choice, or even in the free response, they like to add this in there. They'll say, show that the estimate found in part A differs from the actual by less than, sometimes they'll do 1 over 100, sometimes they'll do 1 over 1,000, just depends. So I'm telling you that this is my approximation, and I'm also telling you that it is close, it is within an error of 1/100th of the true sum. Because remember, this S sub 4, this is my approximation, and I'm telling you that the true sum is within 1/100th of that. Well, the alternating series test remainder theorem says that the fifth term, which would be 1 over 5 factorial, and again, you just get that by plugging in, would be 1 over 120. Well, this is less than that, right? This is my first omitted term. So here, it's the first omitted because I found the first 4, so the first omitted term would be the fifth term, and that would be 1/20th. So then I'm good because I know that 1 over 120 is going to be less than 1 over 100 by magnitude. So I just said by the AST remainder theorem, the true sum minus this has to be less than 1 over 120, and that is definitely less than 100. So I am good there. And I've seen that show up on both the free response and, you know, some of those things in there in the multiple choice as well. All right, moving on to the last page of notes here. So for example 5, given this series, approximate the sum using the first 5 terms. So again, you plug in 1, you plug in 2, you plug in 3, you plug in 4, and you plug in 5. So take a second and you can plug in, and then you get this series of numbers. And then you have to actually add them up. Hopefully this one would be a calculator question, okay, because that'd be a pain to get a common denominator there. So you can add those up and, you know, via your calculator or whatever, you'd end up with 0.839. Okay, so that is an approximate sum using the first 5 terms. Again, how could they make this a non-calculator question? You know, they might change it instead of maybe 5 terms, they can make it just 3 terms, so that'd be a lot easier to do without a calculator. Okay, so here I've got the first 5 terms summed to this, and now it says show that the estimate differs by less than 1 over 20. So I'm saying, is my estimation within 1 over 1/20th of the true? So I know via the alternating series test remainder theorem that the error is going to be less than the first omitted term. So what I need to do is figure out if this is 5, then I need to figure out the 6th term. So to find the 6th term, I plug in n equals 6. So 6 squared is 36, and 6 plus 1 is 7, and that's going to be negative 1/36. So when I go, I say, all right, well, the true sum minus that is going to be less than, well, the absolute value is going to be less than that 1/36. Well, I know that 1/36 is less than 120, so it meets those requirements. And then you're done with that one. All right, so maybe you can pause the video, take a few minutes, see if you can kind of tackle some of those AP questions, and then I will kind of go through them with you, okay? So kind of pause, take a minute, see if you can go through these questions. Okay, so I'm going to assume you've kind of had a little chance to get there. So which of the following series converge? Oh, from the 70s. All right, so right away when I look at these, the first one I want to get rid of is Roman numeral 2 there, because I know that that is 1 over n. That is the harmonic series, and I know that that diverges. You could also think of it as a p series where p equals 1, so we know that that one diverges. So that guy's out. So as soon as I saw that, I'd eliminate anything with a 2, okay? So I can, get rid of choice E, get rid of choice C. And again, remember, your AP test only has A, B, C, D answer choices. Because this one was from, the 70s, they had 5, but you guys only have 4. So hopefully you can eliminate 2 and have a 50-50 shot. And then we will go to, I might take a look at number 1 first, because I'm like, oh, that's a P series, so that's pretty easy. So this is a P series with P equal to 2. And so that's going to converge by P series. So you're like, okay, number 1 converges. So it could be A, can't be B, right? So I'd be able to ditch B, and we already eliminated E and C. So we've kind of got something like that going on. So I'm kind of torn between A and D. So that means I do have to take a look at this one that, looks a little more complicated. So I would go and take a look, and I see that -1, I'd say, it's probably one of those alternating series because I see that -1. So is it alternating? Yeah. Then is the limit, basically try your divergence test. So the limit, as I approach it, well, you're going to have to do that little trick with L'Hopital. So you're going to say, well, the derivative of this thing is just going to be, it's going to be a plus or minus 1. And then when I plug in an infinity there, oh, you don't even need to do L'Hopital's. When I plug in the denominator, I get infinity. When I plug in infinity up there, again, -1 raised to the infinity is either going to be positive or -1. So you get positive or -1 divided by infinity. Either way, that's 0. So check. So it's alternating, decreasing in magnitude, right? That if I started plugging in a 1 and then I plugged in a 2 and a 3, it would be smaller. So decreasing, and that. So that does meet the requirements for alternating series test. And I would say that converges then, and that would make my answer choice D. Okay. What do we have going on in the next one? Oh, this one I thought was a little bit tougher. We'll talk more about this centered part when we get into the next unit. So I probably should have waited to put this one on there, but it's pretty easy. If you kind of look at this thing is going to, when this is think of it as like a right shift or something, so you do the opposite of that number, so that's where it's centered. So if that's true, then you're going to have 0 divided by n, which is 0. So then it's going to converge. So basically what that tells you, and again, we'll get into it more in the next unit, but 0 is going to be part of my answer where it converges. So I know it's going to have a 0, so A and B are out. But let's just see if you would have been able to eliminate the others. If x was 0, okay, so if x was 0, then this summation, if I plugged in x equals 0, you'd have -1 to the n, okay, over this. So that would be an example of an alternating. It's decreasing. And the limit, as you plug in infinity, so again, you'd have 1, because -1 to the infinity is a positive or -1 divided by infinity, so you'd get 0. So we know that if it was 0, you'd converge by the alternating series test, okay? So we know that 0 has to be included. Okay, so 0 must be included, so that means that I can eliminate choice C, because here the 0 is not included. And then I take a look at 2, because that's the other bound on the other answer choices. So if it's x equals 2, then I'd end up with 1 to the n over n, and that's the same thing as 1 over n, and we know that 1 over n diverges because that's harmonic. So 2 cannot be included. 2 cannot be included because that diverges, so that eliminates choice E, so you're left with choice D there. Okay, and quickly the last one here. So what are all the values for x for which it converges? So kind of very similarly, you're going to look at your answer choices. See how here the answer choices are all talking about -1 or 1. So figure out what's going on. If x was 1, then it'd be 1 over n. Well, that's the harmonic. We know that that diverges, so that helps you eliminate a bunch of them right there. And then at -1, it becomes an alternating, decreasing, and the limit is 0, so it converges at -1. So I want an answer that includes -1 but does not include +1. And so that's choice C. All right, have a great day.